Hello, welcome. In this short video, let us look at the derivation of the Fourier series coefficients of the signal component of a noisy data by using the theory of parameter estimation from linear models. That is, given the following observational model, x of n is equal to the sum k equal to 1 to m ak cos of 2 pi kn over n plus the sum k equal to 1 to m bk sine of 2 pi kn over n plus the noise component w of n. Here n is equal to 0 to n minus 1. Values of n are from 0 to n minus 1. Now we want to use the theory of parameter estimation from a linear model to find the estimates for the coefficients ak and bk's. That is, basically we have to convert this to the linear model. To a linear model where x bar is equal to h theta bar plus w bar. Clearly x bar is equal to x of 0, x of 1 up to x of n minus 1, that is the set of observations or the vector of observations. And the parameter vector theta bar is equal to the Fourier coefficients a1, a2 up to am and the second part of the Fourier coefficient vector b1 to bm. Clearly the coefficients a case correspond to the cosine part and b case correspond to the sine component parts. Now the observation model H, the observational matrix H is clearly equal to 1, 1 up to 1 in the mth column and zeros in the m plus 1 to 2m columns. That is, for n equal to 0, we can clearly see that cos of this function basically becomes 1 and here it becomes 0. So we have 1s and zeros in the first column. And in the second column, we have cos of 2 pi by n cos of 4 pi over n up to cosine of 2 pi multiplied by m over n. And similarly here we have sine of 2 pi m over n. And so on up to the nth row where we have cosine of 2 pi times n minus 1 over n. And the last element is sine of 2 pi times n minus 1 multiplied by m over n. And here we have cosine of 2 pi n minus 1 m over n. So this is the observational matrix. The observational matrix H can be rewritten as a collection of two m vectors where we have h1, h2 up to h2m, where the vector hi is equal to a vector of 1 cos of 2 pi I over n, and then we have cosine of 4 pi I over n up to cosine of 2 times n minus 1 into pi over I into I by n. This is for the values of I between 1 and m. And for values of I greater than m, that is for m plus 1 to 2m, we have 0 sine of 2 pi I over n up to sine of 2 times n minus 1 multiplied by pi into I by n. That is the corresponding sine vector for values of I equal to m plus 1 to 2 times m. Thus, we can rewrite the matrix H as a collection of vectors Hi. Now we need to determine the elements of the matrix H transpose H, which is clearly equal to the product of H1 transpose, H2 transpose up to H2m transpose. That is the H transpose matrix multiplied by the collection of vectors H1, H2 up to H2m. And this product is clearly equal to H1 transpose H1. Clearly this product is a scalar, and then we have H1 transpose H2 and so on up to H1 transpose H2M. In the second row we'll have H2 transpose H1, H2 transpose H2 up to H2 transpose H2M. And in the final row we have H2M transpose H1 up to H2M transpose H2M. So that is a structure of the H transpose H when we use the definition which consists of the vectors Hi. Now we have to determine the value of Hi transpose Hj, where I are the values from 1 to 2m and similarly j are also values from 1 to 2m. So we have to find this product. From a previous video we have already shown that since Hi and Hj are basically cosine vectors and sine vectors, from a previous video we have already shown that the dot products of these vectors are defined as follows. That is the sum n equal to 0 to n minus 1 cosine of 2 pi I into n over n multiplied by cosine of 2 pi j multiplied by n over n is clearly equal to n by 2 for I equal to j and 0 when I is not equal to j. And this is valid as long as the values of I and j are less than n by 2. That is, value of 2m should be less than n by 2. And clearly the product H1 or Hi transpose in Hj basically becomes equal to this dot product for values of I and j less than m. But for values of I and j greater than m plus 1, we have the following dot products. That is, for values of I and j both greater than m plus 1, we have n minus 1 sine of 2 pi I n over n into sine of 2 pi j times n over n. This is for values of 1 less than I comma j less than m, and this is also will have the same values n by 2 for I equal to j and 0 elsewhere, that is I not equal to j. Note this is I not equal to j. So these values are valid for values of I and j between m plus 1 and 2m. And for the rest of the values, that is values of I between 1 and m but j between m plus 1 and m, or the other way around, that is when I is between m plus 1 and 2m and j is between 1 to m, we have n equal to 0 to n minus 1 cosine of 2 pi I n over n sine of 2 pi j n over n is clearly equal to 0 for all values of I and j. So by using these three results, we can clearly see that the matrix H transpose H is equal to, or I will have a non-zero value only along the main diagonal, that is when I is equal to j. And for the rest of the values, it is clearly equal to, or for the rest of the locations, the elements are clearly equal to 0. N by 2 multiplied by 1, 0, 0, 0, 0, 1, up zeros up to the final column, or the final row becomes 0, 0 up to the last element where it is 1. So this is clearly equal to n by 2 multiplied by the identity matrix I. Now the parameter vector theta hat, that is the estimator of the parameter vector theta hat, becomes H transpose H whole inverse H transpose x bar. And we already know that H transpose H, that is the product of the observational matrix, this transpose is equal to n by 2 multiplied by the identity matrix I. So its inverse is also a identity matrix 2 by n into I. Therefore, the parameter vector theta hat is equal to 2 by n multiplied by the identity matrix I multiplied by H transpose x bar, which is equal to 2 by n multiplied by H transpose x bar, which is equal to H1 transpose H2 transpose up to H2M transpose, that is the matrix H transpose, multiplied by the observation vector x bar. This is clearly equal to 2 by n multiplied by a vector that has the elements H1 transpose into x bar, h2 transpose into x bar up to h2m transpose x bar. That is the estimate of the parameter vector theta bar. And by using the definitions of the vectors hi, we can write the parameter vector, that is the each element of the parameter vector theta I hat is equal to 2 by n h I transpose, that is the ith vector transpose multiplied by the observation vector x bar, which will clearly have two types of values, for one corresponding to the A case, that is the coefficients corresponding to the cosine, and B case that correspond to the sine components. So we have, that is, since theta bar is equal to a1 up am, and second part of the vector is b1 to bm. So by comparing these two results, by comparing this vector with the minimum variance unbiased estimator, you can clearly see that ak hat is equal to 2 by n sum n equal to 0 to n minus 1 x of n, that is the vector x bar will have the components xn multiplied by cosine of 2 pi k into n by n. So that is the estimate of the coefficients a case. And for the second component of the vector, that is second set of components, the vector theta bar, that is b case, we have bk hat is equal to 2 by n summation n equal to 0 to n minus 1 x of n multiplied by sine of 2 pi kn over n. Thanks for watching.